Okay, so if you can hear my cat in the background, I apologize in advance here. It's late at night and he's kind of used to getting some of his food now, but due to the time change, it's a little bit different. But anyway, so I'm doing these slides. These are supplemental. They're not going to be tested on, and it's going to be in the Unit 3 material that we get into the new stuff. But I did just want to cover these to give you a little bit of an opportunity just to see some other things that are out there, and especially for those of you who may be interested in taking another course like this into the future. But again, this is not material that you're going to be tested on. Some of the things, you know, I've said it throughout the semester so far, is that we're really handicapped in some of what we can do because, you know, the fact that we're virtual. And there's some things that I would love to do if we were in a regular classroom, but unfortunately right now we can't. And you know, this is an example of one. But mostly for this part, I want to talk about, you know, fluid power, but alternative types in this particular section, and then we'll get into some other stuff here in a little while. But fluid power. When I say fluid power, you know, some of you, the term that may come to mind would be something like hydroelectricity, hydroelectric dams, and things like that. But you know, gasoline is actually one of the primary ones that we think about, because you know, gasoline is in its way a liquid, and but we're looking at alternative sources, you know, more cleaner energy sources. So clean energy is energy derived from renewable zero emission sources. So examples: biodiesel, hydrogen fuel, ethanol, electric, natural gas, propane, and methanol. Now, they all have their pros, they all have their cons, and this is not going to be a, you know, which one do I believe is best. This is just putting that information out there, just so that way you know what is available. Biodiesel is a renewable fuel made from biomass, organic material, most of it. Most U.S. biodiesel is produced from vegetable oils and animal fats. So corn, or you know, I remember back home a particular diner that some friends of mine, their parents owned, used to sell some of their used cooking oil to biodiesel companies. Biodiesel can be used in the same equipment as diesel fuel that is made from petroleum. So when we're a lot of what we're talking about here is non-petroleum based. So, you know, petroleum takes millions of years to make. So we're talking about stuff that can be made in substantially less time. Hydrogen is a clean fuel that when consumed in a fuel cell produces only water. So it doesn't produce all of these harmful gases that like gasoline and some others can. It produces water vapor as its output. So if you had a hydrogen engine in your car, you could actually drink its exhaust. Do not, under any circumstances, do that with a normal car. Okay, just, you know, don't. But you know, if you had a hydrogen fuel cell car, but you know, problems with that is if they were to ever get into an accident and explode, it's pretty intense. But hydrogen can be produced from a variety of domestic resources such as natural gas, nuclear power, biomass, and renewable power like solar and wind. These qualities make it an attractive fuel option for transportation and electricity generation applications. It can be used in cars and houses for portable power and many other applications. It's actually, I will say, out of all of these, this one is my particular favorite, but the dangers of it, if things go bad, is really bad, as opposed to a lot of these others. Ethanol is an alcohol-based fuel alternative made by fermenting and distilling crops such as corn, barley, or wheat, and it can be blended with gasoline to increase octane levels and improve emission quality. Ethanol is already in a lot of our fuels today, so you know, you should be familiar with it, at least a little bit. Electricity can be used as a transportation alternative for fuel for battery-powered electric and fuel cell vehicles. Battery-powered electric vehicles store power in batteries that are recharged by plugging the vehicle into a standard electrical source. Fuel cell vehicles run on electricity that is produced through an electrochemical reaction that occurs when hydrogen and oxygen are combined. So we do have a lot of electric cars, and you know, they're good. They're good. You know, they do have their downsides too, but ultimately this is kind of the current, the electric cars and things like that is kind of the current wave on the next innovation of cars. Me personally, I think in the end, I think we're gonna move into some slightly different routes. I go back into the hydrogen, but I don't control the market. And right now, this is a good alternative if you can afford it. I do know some people that have some electric cars, and they absolutely love them. I got to test drive an electric car for a little while, and I did enjoy it. No doubt about that. Well, we also have natural gas. Now, natural gas is not, there once was actually a natural gas car, but it didn't. It never really made it into production. But so you're not going to see something like natural gas necessarily for cars. But it is an alternative fuel that burns clean and is already widely available to people in many countries through utilities that provide natural gas to homes and businesses. My dad's house is heated. He cooks with natural gas. Although, let's be honest, he doesn't cook. His wife does. But they use natural gas. They really love it. I personally, have like an electric stove, and I really enjoy mine. But for most of the people who use natural gas in their homes, they just absolutely rave over it. So that's a good alternative, not for cars, but certainly for homes. Propane, also called liquefied petroleum gas or LPG, is a byproduct of natural gas processing and crude oil refining. Already widely used as fuel for cooking and heating, propane is also a popular alternative fuel for vehicles. I've never seen a propane car, but that certainly doesn't mean that they don't exist. I do use propane for a lot of different things, and and it's a very good source. I do enjoy my propane. And then finally, methanol, also known as wood alcohol, can be used as an alternative fuel in flexible fuel vehicles that are designed to run on M85, a blend of 85% methanol and 15% gasoline. But automakers are no longer manufacturing methanol-powered vehicles. So there are some that are out there and do exist. But again, currently electric is kind of the major wave with cars. Okay, so these are just a couple of clean, quote unquote, clean energy fuel sources. I'm going to do another presentation here in just a little bit on just some other things to kind of wrap up that second unit that we're going to see. That will also be optional. And then later we'll have our Unit 3 material, which will be the stuff that you will really need to take notes on. Hello and welcome. This is the second of 3 videos that I'm putting out that are not required, but I strongly encourage that you watch. If you're watching it, obviously you're already here, so that kind of goes without saying. But this is some stuff that we've actually already talked about, and so I'm going to move through this very quickly. But the idea of documenting the design process, I spent a lot of time talking about this earlier in the semester when talking about how to make presentations and pros and cons and different things that you really need to look for. So documentation of the EDP is essential so that the solution can be communicated to the intended audience. Okay, so it's not just it's one thing to be able to do the work and be able to present, to be able to create the product, but you also need to be able to communicate those results. You can have the greatest product in the world, but if you can't tell anybody about it, or nobody else can take what you have done and be able to manufacture it, then it's not going to do you any good. So each step in the engineering design process should be recorded in an engineering journal. This is something that we have not worked with a lot this semester, just simply because of the situation that we're in. But in a standard classroom, we would be doing a lot more working with this journal. But the long story short, if you are working on a project, anything and everything that you do needs to be really needs to be journaled. I'm working on my home styler project, and for the life of me, I cannot get in the bathroom that I created in the master bedroom, I cannot get the shower to align up right, and I don't know why. I don't know what's going on. That would be something that I would be documenting in this journal, so that way somebody who came in after me could look at it and they may automatically know what to do to fix it, or if anything, it at least lets them know that they need to adjust, and they need to be on the watch out for this because it might happen to them as well. This record serves as the author's proof of work and will be used to help present the solution. So lots of good things within that. A journal can be kept as a physical record or as an electronic record. Since we're doing everything virtually, electronic would of course be the way for us to go. Either format must include the author's day-to-day activities and showcase major accomplishments as he or she works through the process. Now, by day-to-day, if you're working on something, odds are you're working on it every day of the week. But if it is something that you're working on in your casual time, and you may go an entire month without it, then you would want to, make a note each time that you return to it, how much time has passed, since you worked on it. Just that way, an accurate timeline can be made from all of that information. It is essential for engineers and designers to present their work, okay, if anything, just for the patent. And while the audience may vary, the ability to formally and informally articulate ideas, successes, failures, and design solutions will help gather feedback and determine the final solution. So, you've got to be able to explain to people what you did. And that is one of the toughest things to do. I remember many times, part of teaching math, something that I like to do whenever time permits is I would have students teach a lesson. And it was very much an eye-opening experience for them, because it's one thing to be able to do the work, it's another thing to be able to present it. So, and our final exam in this class is going to involve some kind of presentation, and it will be a graded presentation. So that's something that you're going to have to keep in mind while you're working on all of this. Prior to the presentation, determine the target audience. So now this is something that even for one project, you may have to alter your presentation multiple times depending on who you are presenting it to. So your home style project would be a good example, because you may, you're going to be presenting it to me, but if it was something good enough, we may want to take it to some of the principals. And so you might want to fine tune some things for them, some things that they would not understand that I do, and so you have to change your presentation depending on who your audience is. Presentation purpose. Is it a persuasive argument? Is it to inform somebody about the project? Is it, whatever it is, okay, that purpose may guide how you do your presentation. And finally, the presentation format. Is it going to be electronic? Is it going to be handouts? Is it going to be a poster? Is it going to be a poster board? Is it going to be a billboard? And all that kind of different stuff, because that's really going to change what you do. During the presentation, always introduce yourself. Don't assume that they know who you are. Recap the design process. And so in some way, shape, or form, you need to include all 5 ideas. Discuss successes and failures. Okay? The successes is great. We all like to succeed. We all like to, for people to praise what we have done well. But most of the time, especially when you're trying to pitch something to somebody, it is your failures and how you respond to your failures that actually means more. So you do need to include your failures. Include visual aids appropriately. Don't overwhelm people with visual aids, because in a presentation, you are the star, not the visual aids. So you want people looking at you. And then leave time for questions. Don't run it up until the very last moment where nobody wants to ask any questions. Okay, always leave time for questions. At the end of the presentation, summarize your main point or points. Leave time for questions. If it is something where there is a required time amount, always leave filler. Always leave something that you can talk about if you have to fill time in case nobody has questions. But if you do your presentation correctly, there should always be questions. Be sure to arrive prior to the audience. You need to be there. You need to be there before the audience really starts getting there. Speak clearly. This is something that for me, especially when I get in a hurry, I have a hard time with. So slow down, enunciate, and practice. Don't just excuse me. Don't think that it's just something that you can just do off the cuff. You need to be ready. You need to be rehearsed. You can, if you go back and watch my presentations, you can tell the presentations that I spent a lot of time thinking about beforehand, and in the ones where I understood it, and so then I just kind of went right into it, because you're going to hear a lot more flaws in the one that I was better prepared for. I mean, that's just the way things go. So practice, practice, practice. Okay, welcome back to the third of 3 videos that are kind of optional for this class. We're still talking about the design process and documenting the design process. Now we want to take a look at fluid technology and how it combines with mechanics and the omnidirectional nature of fluids. So in other words, how fluids actually help us, in a day-to-day life. And the most common one that I can think of is hydraulics. We're kind of talking a little bit about hydraulics and how it works. So fluids have a loose molecular structure so that they flow and take the shape of their confining container. They can be gases. Now this is kind of a weird one to think about. There's a course at NC State called Fluid Mechanics. If you're, say for instance, a mechanical engineer, but if you're an aerospace engineer, the exact same course takes on the name aerodynamics, because whether you're talking about water or whether you're talking about air, most commonly you can put like a little bit of smoke into air and move your hand through air, move your hand through water, and what you'll see is that they move in virtually the exact same way. So when we talk about fluids in engineering, you may be referring to gases, you may be referring to liquids. So controlling gases under pressure is called pneumatics, and controlling liquids under pressure is called hydraulics. Oh, look at that word sounds familiar for some reason. Okay. A fluid exerts a force. Sorry about that. Exerts a force to all inside surfaces of the container holding it. Pressure is measured as a force distributed over a specific area. For example, pounds per square inch. So the force is pounds. We tend to think of pounds for us in terms of weight, but weight is how we interpret in the imperial system. What we use in the United States. It is mass under the force of gravity. And that's something, if you want me to, I can talk to you about it, at some other time. But pounds is a force, and such as a force that we use to measure pressure whenever we measure it over an area. Pressure is caused by the cumulative force of random molecules of a fluid striking against the inside surface of a container. So again, remember, fluid is both gas and liquid. Okay, so when I'm talking about the balloon, and we're talking about the pressure that's inside the balloon, we, at least for me, when I was, first, before I had really learned all of this, and I thought of terms of things like pressure, I thought about this like solid object inside the balloon, even though I knew it was a gas. But what it actually is, this idea of a cumulative force. Pressure is the summation. If you were to add up every individual molecule or atom that is inside that balloon, and it's actually those atoms hitting against or interacting with the atoms and molecules that make up the balloon. And so it's not just this one thing inside the balloon, but it's a whole bunch, billions and billions and billions of tiny molecules that are actually interacting with the rubber of the balloon and bouncing against it, and that's what keeps the balloon open. If for some reason all of those molecules were to shift over to one side, the balloon would actually sink in on another. It's kind of an interesting thing to ponder. Liquids do not compress. That makes hydraulics very useful in efficiently transmitting forces. So in other words, what we're saying is, if I were to push water through a tube, like if I were to take a tube and close it off and blow into that tube really hard. Think of something like a PVC pipe, and you were to cap it off and you were to blow into that PVC pipe really hard. In theory, you could blow even harder and push more air into it and start to compress it. I mean, this is done all the time in gas tanks, scuba diving gear and things like that. But liquids, because they do not compress, or they don't compress nearly to the extent of something like a gas does, then if I put a whole bunch of pressure, a whole bunch of force pressure is not a force, but if I put a whole bunch of force into that, then that liquid, since it won't compress, that means it either has to like get out of the way and so it'll like splash back on you, or all of that energy then gets transmitted into the pipe. So there's real interesting explanation about what's going on in the movie The Score with Robert De Niro. But I'll leave that one up to you. Pascal's law. Pascal experimented with fluids during the Renaissance. That should sound familiar. And Pascal's law states that the pressure at any point in a body of fluid is the same in every direction, exerting equal force on all equal areas. So the pressure is the same, and any change in the pressure at one point in a confined fluid will create an equal change everywhere in the confining vessel. So there was an example that I saw of this where they tie a weight to this very, very, very large styrofoam head. They made this kind of like a totem out of styrofoam, and then they drop it in the water, and they have this weight on it so that way it won't float and it sinks. And they let it drop down and down and down into the water. And then after a certain amount of time, they then pull it back up. And when they pull it back up, that styrofoam head had like compressed into such a small amount, but it was a perfect miniaturized replica because the pressure that was squeezing that styrofoam closed was the same in every direction. So it never dented or punched into the styrofoam. It shrunk it equally. So it was a perfect miniaturization of the original totem. Hydraulic cylinders. These two fluid-filled cylinders connect by a hose represent one fluid container. The piston inside each cylinder can slide, forcing some of the fluid from one cylinder to the other, pushing the piston and solid rod outward. Because it is one container, Pascal's law will apply. So in other words, if I push down this cylinder on the top, all of that energy that's getting pushed onto this water is going to translate perfectly into this cylinder down here at the bottom and then push that piston out, and vice versa. If I push this bottom piston in, it's going to push this top piston out. If we apply 5 pounds of force downward on the top piston rod, 5 pounds of force should push out on the lower piston rod. This is because the increased pressure created by the force and the top cylinder will be transmitted equally to the bottom cylinder. This transmission of force will work with a flexible or rigid hose on almost any reasonable length. Extremely small or long connecting hoses will create efficiency robbing molecular friction. So what this says is that if I have a really long hose, I don't know what the requirements are for extremely small, I'll be honest, but I know an incredibly long incredibly long hose. The thing about it is that as fluid moves through this piston, is that there is going to be friction there. The fluid is going to rub up against this hose. It's not 100% how friction works, but it's close enough. And so the longer the hose, the more the friction will begin to have an effect on the transmission of energy. Now, for some things, those lengths may be in terms of miles. As a matter of fact, if you were to look at like natural gas lines, because these travel hundreds and hundreds of miles, they actually have to have vent ports to give the opportunity to let the gas cool down. Otherwise, there would end up being so much friction buildup that it could actually ignite the gas. It would create so much heat. Fluid mechanical advantage. This is something that you hear a lot in engineering. You hear about stuff called mechanical advantage. If we vary the size of the piston from one side of the hydraulic system to the other, we can easily create a tremendous mechanical advantage. In other words, so there's a whole lot more volume here. And let's just say that there's twice as much volume in this piston down here at the bottom than here on the top. So if this piston moved 1 foot, now we're just assuming twice the volume, not determining necessarily how. if I move this piston 1 foot, then it would move 2 feet in this other piston. And so that's what we mean by mechanical advantage. That's because the force is only one factor. The pressure area is another. Remember that pressure is force divided by area, and Pascal's law states that the pressure is the same in both cylinders. So twice the area ends up resulting in twice the force in the area that's half the area, right? But the area that the pressure pushes against is different in these cylinders. Example, if the larger piston surface is 5 times that of the smaller cylinder, the resulting force will be 5 times greater. Okay, I just stated that earlier, but with 2. So Pascal said the pressure of the input cylinder is equal to the pressure of the output cylinder. This is what is really important right here. Pressure in has to equal pressure out. So, and we know that pressure is force divided by area. And force divided by area in equals force divided by area out. Assume that the input piston area is 1 inch squared, and the output piston area is 5 inch squared. We assume we apply 2 pounds of force in the input cylinder's piston rod. 2 pounds divided by 1 equals force out divided by 5. And then when you run through these calculations, you got to multiply both sides by 5 square inches. You get force out is 10 pounds. Okay. These fluid technology principles are applied to many engineering solutions, from backhoes to elevators and lift gates. You know, heavy machinery. If you hear heavy machinery, you know, think hydraulics. Okay, so that's going to that's going to be there to help you out. So that's it for these. Again, they are just they're real quick. They are you know, it's just totally supplemental information. This will not be anything that you're tested on. The next lesson, though, you are going to want to take notes. I hope that you enjoyed these videos, and you know, thank you for watching.